this is being used in all the protection relays, and also the same way test kit manufacturer also use these compensation in their software. So because in template you cannot change much, so that is why you need to understand all these things so that you can create your own template without help of manufacturer. So maybe in practical session I will create all these things. So tomorrow we have a hands-on on relay. So for on relays also we will explain these not all combination, at least two which is very common, TY and star star connection. So we can demonstrate all these things, how to test the differential relay. We can create this test plan manually as well as with the help of template, so that you can understand all point. So any manufacturer relay test that you have to follow the same thing and do the testing. So uh, single PLC so and now the how we can vary the bias current, you already learn it. So if we decrease one side current from here, then this point will move like this. If we will increase, then this point will move like this. That is why I said, so you should know these two slope turn point, so that all the bias current should be in this range, so that when you calculate the slope, it should be correct. So if you do not want to move this point, then you have to increase from one side, decrease from other side, and the ratio should be same. That is that is also condition. Because if you are having a different ratio, then also this point may move. Suppose it is a 33 132 by 33, the ratio is 4. Suppose you have increased point 1 in one side, then other side you have to reduce 0.4, because the current ratio is 4. Okay, so to keep this bias correct, in software, if you see when you yesterday I was demonstrating in the software, then in software automatic injection is there. So they they uh, they search this point with changing the both side current. There is a phasor option also, I will demonstrate later. You will see that how current is changing. So first they inject one current. If relay is not tripping, then they increase or decrease, and based on that differential current increase. So this point move like this. So if relay tripped, then it move again down. So and settled at the exact boundary point. If we are decreasing one side current, then it is moving like this. If we are increasing the current, then it will be moving like this. Sometimes if you will not uh, the bias current in the relay, then it may move like this and it may never go to the slope. So you have to take care these things while doing the manual testing. In automatic testing, everything is calculated in the relay itself. So these all guidelines for when you are testing the manually. So in this case, varying both current to keep the I bias constant. In all the relay, you will see relay test kit software, you will see the point is moving like this. When we select any point anywhere, then it will move like this and find out the boundary point when we are doing the characteristic test. This is called binary search. One point injected, if it is stripped, then they will move the then they inject the other point up and down, depends on the, if it is non-operating region, it is operating region. Point always move from below to above side. So if relay tripped, that means you got the boundary point. So they reduce the current slightly. First step to find out the current is bigger. So when it tripped, they reduce the current again to and move this point to lower at towards no operating region. So if relay is still tripping, then again reduce the current, then so that the exact boundary point can be find out. So once they find the exact point, then it is pass fail indication that relay passed the condition. You can see how it is. And this characteristic is of SEL 487 relay. So all other relays are okay, but nowadays some manufacturer is having this dynamic type of characteristic relay. So we have seen that the characteristic is like this mostly, but in a CL 487, if you see, they have this characteristic, and if CT saturation, all these condition happen, then this move to here. So this is the all dynamic characteristic, and I think in any Siemens relay also they have implemented. So this characteristic is based on the situation. So what they consider in this, CT saturation does not occur immediately, but will take more than 2 milliseconds. So relay has time to detect it and switch to slope 2. So if CT saturation condition you are injecting, so that means during testing we have to give this delay so that this slope move to here, because we want during CT saturation condition relay should not operate. So in this case it was very easy. We do not need to change anything. Uh, in this also, if it is in the actual condition, so as per the algorithm, relay will calculate and check the characteristic. But during testing, if we need to check this situation, then we need to provide this delay to differentiate between this. That is why many customer has this problem during the testing. So this dynamic characteristic is slightly different from this one. So when you are following the normal uh, testing method, then you can find out this and this slope by that way. But finding this slope too, you need to have another algorithm and creating this situation. So, so how it is tested? It can be tested through state simulation method. State sequencer, state simulation means we create the different state so that we can implement this delay. As I said, if delay is there, then the relay algorithm think that it is a CT saturation condition. So this slope will move to this slope. So we are doing through the templates. Many has made this template as well, but Doval do not have this template. So we use it for slope to testing. We have to use the state simulation method in that case, because if there is no delay, then we cannot achieve this slope. So we can create a one mm, uh, balance balance condition state. In other case, we create the fault with some delay, implementing some delay. So this slope test can be achieved. Here you can see that this is normal condition and it moved there at this condition. So we can achieve this, and we can verify that the during this dynamic condition, this slope is not uh, uh, this slope is moved to this place. If suppose we have given some fault here, so and through this dynamic state testing, then at this place this differential relay should not operate when we are creating the CT saturation condition or giving some delay. So this way we can test this dynamic slope condition. Anyone have this relay? SEL 487. So it is 90% relays, 95% relays have this characteristic only, and it is very easy to test. You know all these things. Only one Siemens model and this SEL model has this dynamic characteristic. So we have a modern test set. We and software for storage of the result. It is nowadays very easy to test any relay. Just use the template and you can test any relay. And we can have a graphical visual display, all the bias and differential current detail, how it is moving. Everything we can analyze in the these new relays. Earlier these were not possible. So every manufacturer has relay library model, and they also assist in if the relay library model is not there. So, but the purpose of this training is to provide insight so that you can create all the test plan yourself, not depend on the manufacturer library models. So this is one template in which you can enter different data. can see this is the condition where based on the selected point we can we can see that we selected different point at different slope and just run the test and you can also visualize how primary secondary current is injecting in this particular case. So these are different test method we have discussed in this. So it is just concluding. So there is still left the harmonic, how we test the different harmonic condition, it is working properly or not, that we will discuss again. So this primary condition to test the differential relay, we should have six sources for testing these characteristics. So if these libraries and test modules all are available in your software what you are using, then it is very good. You can do all testing easily. But if it's not available, then try to learn through these concepts. Create yourself if you want to explore more. Now, the second and fifth harmonic feature testing in transformer differential relay. We should understand this. So there is a harmonic restraint, harmonic block. So when we have this setting in the our all relays. So because whenever transformer is charged, then the second harmonic current is predominant. It will be always there. So it may have 2 times of rated current to 8 times, 10 times, depends on the size and manufacturer. So during starting, we should block this, otherwise transformer will trip immediately when we will charge. Most of, if you are in the power sector and frequently charging the transformer, then most probably you have faced this problem. So even though sometimes everything is okay, in that condition also sometimes other protection do not have the harmonic blocking, then that tripped. So this harmonic component, how it affect the our testing, our transformer charging condition, we can understand in this case. So what is the harmonic restraint differential? Harmonic restraint. Suppose our setting in the relay generally 15-20% for a second harmonic. Okay, so what is the restrained harmonic? So if the harmonic component present in the system is less than 15-20%, then it is called restrained harmonic. So that means if this much harmonic is available, then it will be add up in the differential operating current. If suppose differential setting is 0.3 and this component is 0.1. If operating current is 0.2, then it will add up, and if addition of this is more than the operating current, then the relay will operate. Okay. So it will be added in the differential current in this case, in the restrained condition. So here also you can see from the formula operating current. This is the fundamental current, and these are the harmonic components. These all added, and if this is more than the operating current setting, then the relay will operate. So here the meaning is there. This is operating fundamental component of operating current. Second, third, higher harmonics for operating current. It's the unfiltered operating current. K1, K2 are constant of percentage setting. Slope I is for percentage. So from this formula it is clear. So if it is a restraint condition, then everything will be added, and if it is the added values is more than the set operating current, then relay will operate. Okay. Now you can see it through graphically. So actual condition this will be this, but if a harmonic component is there, a restraint component is there, then the slope is like this. That is why the final slope will be like this. Okay. So this is being added, and this is the final slope. Here also you can see through the diagram. This is the I operating setting. So these all components has been added. If this is more than this, then it will give the tripping command. Okay. Anything, any question if you have till now? This is very simple. There is nothing to add in this, because just adding all the current, if it is more than the operating current, this relay will operate. Now the second condition is the harmonic blocking, which we require to test blocking and unblocking condition both. So in differential relays, each selected harmonic blocks the output of the differential element if its magnitude is greater than the percentage specified by the constant. Like in this case, if suppose differential current is 0.4, and with this our operating setting is 0.3, right? And differential current is 0.4. But with this, if we have this differential current, the differential will operate, right? Because it is more than the operating current. But suppose with the 0.4, we have suppose 0.2 harmonic component, second harmonic. Okay. So the differential current increased from the set operating current, but relay will not operate in this case. Although the operating current, actual operating current, fundamental operating current is more, but if with this will present, then relay will block. It should be more than this setting. So maybe we can put it to 0.8. We have increased the differential current more. In restraint mode, you have seen that the both current has been added, but in this case, we have much more than that current, but still relay is not operating, because we do not want in this condition to trip the relay. This second harmonic component present only at the charging condition. In fault condition, this second harmonic current will be generally less than 10%, not more than that. That is why, based on the experience and fault analysis, we can say that during fault condition, this harmonic will not be present. So we should block this condition.
Okay. So we have to select either one, working or straight.
No, no, it is permanently in the relay. If you are enabling harmonic, then both are. So, so we are testing these conditions. If you have tested the harmonic test, then what we will do? We inject the fundamental current and harmonic current, and we reduce the harmonic current from, suppose we have started 50% of the harmonic current. Simply understand, 1 ampere is the fundamental current, and setting is let us say 20%. 20%. And you have started the harmonic current also from the 1 ampere. 1 ampere is, it is a 0.4, let us say 1 ampere. It should operate immediately in normal condition, because it is much more than the differential operating current. And we have added 1 ampere second harmonic. Now what happened, we keep this constant and reduce this in the ramp method or manually, whatever way you want. When you reduce it and reach at less than 0.2, then immediately when you are going to less than 0.2, immediately differential will trip, because the operating current is already enough to operate the relay. It is blocking because the second harmonic is present. So as soon as this, so this 0.2 is restrained region. Below 0.2, it is restrained current. So that means at 0.2, what will be the differential current? 1 plus 0.2. So it is added. As soon as it is come in the restrained region, it is being added. So it is in all relay, by default both will be there. So in this testing, we have to reduce the harmonic component at the so that it will come to the restrained region and released. So we confirm that it is blocking for more than the our setting, and unblocking at that, at which point. Okay. So any confusion you can ask. And similarly for the fifth harmonic, testing is exactly same. So what is a second harmonic? If it do not require any test plan or anything, you can manually control all these things. Suppose you have one component, this is 1 ampere at 50 hertz. If it is a second harmonic, if it is a 60 hertz system, then you have to select 60. Then harmonic component will be, suppose we are starting from here, then it will be 1 ampere at 100 hertz. Correct? If you have a 60 hertz system, then 120 will be there. Okay. So we have a 3 current set. This 3 current set. So we keep it constant and reduce this. So if setting is 0.2, then exactly at 0.19, it will trip, Sometimes 0.2 will may also trip. So it will be in this range. 0.19 definitely it should trip as soon as it will reduce from this. So you need only 6 current, or there are different method, many ways you can test this harmonic testing. So I explain 3 method how you can test. But the basic one is the to understand you have 6 current, you can reduce one with the second harmonic component and keep the other constant. So suppose this current, if we have 0.5, then at which current it should trip. Suppose a 0.5 is fundamental current, then at which current it should trip? At a point 2, point 2. Huh?
0.7.
No, no. I just want this harmonic component, not adding all these things. So how much current it will take? Why 1? It will block because our setting is 0.2 to 20%. So the 20% of what? Fundamental current. It is not like that it will every time it will trip at zero point 0.2. So suppose it is 1 ampere, then it will trip at zero point 0.2, standard zero point 0.2. But suppose you have decreased at zero point 0.5, then this will be 0.1. The percentage of the fundamental current, not it is fixed at 0.2. It depends on the fundamental current. If you increase it to 2, then the blocking will be at 0.4. The percentage of fundamental current it will be. It depends. Okay. So it is generally confusion when you are testing. That is why I asked this question. So always test. So generally we do the testing at rated current. So if you easily want to test without being confused, so always inject 1 ampere. So it will be 20% injected. Okay. So this way you can test the harmonic. Basic understanding. Here you can see this is a blocking. So if there is no harmonic current, then this will be 0. 0 means this is a AND gate. This will be 1 as soon as the operating the current calculated in the relay more than the set operating current, it will give the this command and relay will operate. But in case second harmonic present, any second harmonic or fifth harmonic, so this is OR gate. So this will give the blocking command, and it will be now 0. So even though operating current is there, but it cannot give the tripping command. This is the simple logic. It is implemented in the same relay, all relays with the same way. Okay. Any confusion in this? Okay. Let us do some methods. There are different method of detecting, and there are these features also in the relays. So one of them is a cross blocking feature. So some people enable it, some do not enable it. Let us understand all these things through some example. So in this case, so independent harmonic blocking. So each element block only that element. If harmonic present, like if we have
The human is the face. Human is that face.
yeah phase, so that's why I am drawing it. Let us just draw three lines. I'm not drawing it properly. Just this is neutral. This is suppose R, Y, B. So all the elements. This is element one. This is element two. This is element three. Okay. Yeah. One, two, three. This is what explain. Suppose the fundamental current is 425. The restraint setting is 20%. Okay. Second harmonic current is 180 ampere. So how much percentage you can calculate? I have already calculated here. So it is how much? 42.3%. So harmonic current is more than the our setting, so it will block, right? In second case, it is 125 ampere. So if we divide, so every time you can see that it is taking reference of the fundamental current, not the rated current. Okay, whatever fundamental current is there, it calculation is based on that. So here, although if it is the transformer, then all windings should have a same current rating, and we should have taken the same reference here. But we are taking the fundamental current reference. So here 125 divided by 670 ampere. So it is 18.6%. And in element 3, there is 230 divided by 435. That is 52.9%. So in this, in both case, element 1, element 2 will block and element 2 will trip, issue the tripping current. Okay. So any element is tripping, then the differential relay will trip and trip all the both side breaker. Right? Is there any confusion in this? This case is when we have set independent operation. Okay. Now cross blocking is there. If we consider the same case, and we have enabled the cross blocking, then in this case what will happen? If any element is uh, uh, blocking, here two elements are blocking and one element is not blocking, it is in the restraint region, so it should issue command. But in cross blocking, all three should trip. then only trip. If any phase has harmonic blocking, then it will not trip. Okay. So in this example, the same condition is there. In one case, the relay tripped. In other case, relay do not trip. So it has a lot of confusion. We should enable it or disable it. So sometimes what happen in one phase there is a no harmonic present as much as in other phase. So you would have seen. So if a cross blocking is enabled, then it will block. And if it is normal condition, then it will be blocked, and it should work every time. But I have seen practically in one case there was interturn fault condition. In that case, it was in operating region, and the fault was there, but due to other two elements was blocking, so really didn't trip, and it takes long time. So most of cases it is useful, but sometimes it create problem as well. So we should decide what to, but most of cases cross blocking is enabled. But looking at that incident, I think so we should not enable cross blocking. Then that also create problem sometimes, relate trip, and it create confusion. So we have to balance it. So it has advantage, disadvantage. Recently, last year this case was there, and in some relays also it happened. I will not mention manufacturer. So I contacted manufacturer and informed him that your relay mal operated in this condition. There was three cases. I shown them. They told that the relay is not mal operated. It is working well. And since 4 months we are following, but still not received the answer. so so that is why it is quite confusing. We should enable cross blocking or not. So, but you understand the concept. What is okay? If any question, you can ask. So this is how it is. So it's a winding one secondary current in data acquisition. So it is divided in different component: fundamental, second harmonic, fifth harmonic. So it is added the tap setting as per our setting. Uh, then correction compensation, like we learned yesterday. So all these steps, now we have all components, and after this component available in the relay, they compare it as per the logic and settings, and issue the command. So here you can see the unrestrained component. It do not have anything to do with the harmonic. It straight away. So you understand the unrestrained current. Yesterday I explained, but explaining it again. Like I said, for differential setting, so so for differential setting, for this case, it is a pickup test what we do. So from here to here, high bias current is considered. Okay. So, but when differential current is more than the set limit here, this is called unrestrained. Restrained matlab, Restraint means it is uh, uh, restricting. Unrestrained means it is independent. So as soon as the differential current value is more than this value, so we do not consider this value. Immediately trip. Suppose how you can test this. So here, suppose I bias current is 10 pu in transformer case. So you inject from both balance current from both sides. The I bias would be 10 pu or whatever it is, where it is coming. So the relay should not trip actually, because differential current is not there. But in any case, if a differential current will be, if we test through the state simulation, then any case it is more than this, then it will not consider this bias setting. It will give immediately the tripping command. So just before this, if we will check at this point, then it will block. If it is just this point and this point, if we consider, then it will block. But at this point, as soon as reaching at this point, differential current, then it will immediately trip. So, so this way, the reason why we have unrestrained differential, because if differential current is much higher, then we should protect our transformer first. So that is why at a certain limit, that is why the value is generally 8 times to 10 times. That is why it is kept at higher place. Even though if it is a nearby fault, in that case through fault, then also we want our transformer to protect. At the terminal fault also, we do not restrict our transformer to be in service. Otherwise, it may have, due to so much high current, there may be mechanical damage. Although there is no internal fault, but mechanical damage may take place. So that is why in this case we want immediately transformer to trip. Okay. So that is why this unrestrained component is independent of this harmonic. Whatever the harmonic value and all these things, it is independent of this. It immediately give the trip command if the differential current is higher than the setting. Okay, so restraint current is from here, and second harmonic blocking, fifth harmonic blocking, these all combined, and as per the logic, and give the restraint trip command in all three slopes. It is clear now? Now, how can we test the second harmonic? So there are three ways we can test. So the first, you can see I have injected this fundamental current. Winding 1, winding 2. So from here, I will inject this 50 hertz component, maybe 1 ampere, secondary 1 ampere. Okay. From here we inject second harmonic component. So 1 ampere. Okay, so this is the condition. So let us take the yesterday's example. What we have, what was the rated current in primary? 0.73. Okay. Here, what was the rated current? 0.84 or something. Huh? So, in this case, so we are injecting from secondary and this is from primary. Okay, so let us inject this fundamental current, rated current, not 1 ampere, so that you can understand exactly what I want to say. Okay. So now, if we are injecting this way, then we reduce this second harmonic value in this. So as I said, there are 3 differential component here. Okay, or YB. So whatever differential current is, operating current is already present in this. We are just a relay is blocking just due to this harmonic component. We reduce this values, so it will trip when it is less than 0.2%. So in this case, how much current how much current it should trip? Can we calculate? So it will be 20% of 0.73 or 0.84 in this case. So this one is different case. So how we can do this? 3 methods are there. Now second method, I have okay. So this is winding 1, and the same current is and with the okay. So this current we can inject from the same winding. We can connect both the sources in the same winding. Okay. So here current you can consider 1 ampere. 1 ampere, and it is at 100 hertz. So both method is correct. Both way we can test the harmonic blocking. So in this case, the current is fundamental current injected through HV winding, and the harmonic current is also going to the same component, but it is through the LV winding or winding 2. Okay. So, and in this case, both the we have connected 6 sources at the same terminal. One having the fundamental current, other having second harmonic. So both are okay. You can test with the both method manually. But what should be the current, operating current in this case, in both cases? It
Zero
should be same.
less. Second case is less than 0.146.
So how you have calculated?
Uh, this 0.73 is considering as 100 percentage.
Mm-hmm.
I make this 20 percentage. Usually we do like this.
No, it is actually not. What you have calculated, it is true in this case.
Yeah, second case.
Yeah, but in second harmonic component injecting through the second winding.
First case usually we don't follow the first case because for second harmonic we consider interest in starting time. So starting time secondary side we always consider no load condition. So for second harmonic normally this is actually my testing method.
No, ultimately,
Yeah.
ultimate HV side. What do you mean? If you are in a solar plant, both are
Yes,
in
yeah.
night. It is generating.
Correct. Load always. Yeah.
So it is not the case. So the differential relay will also work. You can even suppose you have 400 by 220 kV.
Okay.
Can we not charge from 220 kV side?
Yes, can.
We can.
But I usually do this
Generally, practice is this
yeah,
one. Yeah, it's correct. But this way also you can test.
But I never tried this way. But next
Yeah,
time
if you will try, then you will find that this in this case this percentage will come.
Okay.
Because it is per unit.
Okay.
Per unit in transformer we calculate it per unit basis.
I have one question.
Hmm.
Normally it has to take from fundamental frequency,
Hmm.
but in secondary side we are not injected fundamental frequency,
Hmm.
but still it takes from what basis it will take.
So actually it is calculated here in coil. I have shown you the diagram.
Okay.
Ultimately current is going to the operating coil. So there fundamental current is also going because it is all differential current.
Yeah.
What?
Yeah, I understand. The fundamental frequency now is this 0.73, correct?
Hmm?
Now the fundamental frequency, now the operating coil get is 0.73.
Yes.
So from the
Not
fundamental
0.73.
Okay.
Actually, see the previous slide. What happened here? You see.
Okay.
So either you are injecting in winding 1, winding 2. Ultimate this component is coming after this.
Okay.
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 So either it is winding 1 or winding 2. These values is after this correction factor.
Okay.
So like basic differential concept.
Okay.
You are injecting and finally this is the after conversion and compensation. This is going to the differential component.
Okay.
Okay.
But the fundamental frequency is in wind LV side, HV side.
No, it is either LV or HV. That
Okay,
doesn't
okay.
matter. Ultimately going to here.
Okay.
Okay. So this is how calculated. It is also fundamental.
Okay.
Okay. So after this conversion, these values analyzed, not just add injecting.
Okay.
So actually, what you have injected, that is converted in you can say per unit, and it is in per unit. And even if you see the measurement, that's why I said in transformer you will find it in per unit.
Yes.
Right. So this way, here you can test, and opposite is also true. You can inject fundamental current here, and that is also a method. Any way you can test.
So in this case, when we inject fundamental in HV,
Hmm.
that will be same pickup value 0.14 for same value.
Here it will be same
Same.
because there is no confusion in
Yeah.
this. So it is clear.
Yeah.
It is just same winding. There is no confusion.
Okay.
That is why we suggest this one. So mostly it is just for example. If
Okay.
you are doing this, so always suggested this one so that even who is reading report he may not be having this idea.
Yeah.
So he may think that it is wrong. So, but this is also correct. This is also correct.
Okay.
You can test anyway. And there is a third option also.
Third. Okay.
Yeah, third option because we have advanced software now. In only 3 current we can add
Understand.
the harmonic also.
Okay.
So I will demonstrate in the after this session.
Oh,
Maybe
9 source current.
huh?
No.
Not
Super
only three
source.
source.
Only three source.
Only 3 source you can use. So this will be 0.7 plus, like I added the second harmonic, even fifth harmonic, even 10th harmonic. You can add anything at a time, only in 3 source.
Just like state
Yeah,
sequence.
as I have shown the equation.
Okay.
So you can add multiple component.
Okay.
The protection suite advanced software, not in 3.0 version,
Okay.
fifth version, and even in all other manufacturer software, these options are there. I will show in protection suite
Okay.
how you can add a different. So this way also you can test. So these are 3 methods. It is in the slide also. So I think it is clear now what I. If anyone else have any question, please ask. So this case is what I have shown here. This one, all both are connected in same winding. It is a W2. So no, it is W2. It is a second case. This one. So here both are going in operating coil W1 plus W2. The combined waveform of this will be look like this. Depends on the value of this winding to current. If we are injecting equal, then most probably it will be like this. When we reduce it, if we get the tripping, at that tripping time, the waveform will be not so much distorted because it is near to the fundamental current. When we have a equal value, then easily you can identify the second harmonic. So how we test? Here, this one is the first method. What is followed? 3 sources connected to the both sources connected to the same winding, like here, and we will keep one constant, other reducing, like this. So when the relative expected is 20%, so it will trip at 0.2 because we have taken 1 ampere reference. It is 20% of 1 ampere, or so whatever the rating, it depends on the current rating. So here we consider it, so it will be at 1. During this method 2, in method 2 you can see earlier Noble has it. This is old software, but in new software also, this one is a free if you want to try but not sure it will be working in the Windows 11 or not. So here, that's what I said. Uh, the third method in which you can add the in three sources itself you can add a different harmonic component. Here it was option to add harmonic in this. So here you can see the whatever harmonic component you want to add, you select that harmonic, how much percentage you want to add, percentage value in voltage or current. Here we need in current, so we added 30%. So, so if it is 20%, so we add more than 30% to check the blocking. So even at the same time you can add the fifth harmonic also if you want. So this is a very easy tool and now available in almost all manufacturer software. So we need not to connect the six sources, either one side or two side. Any side you connect this, and it is very clear from the these uh, these values. We have fundamental current here, and we added the second harmonic component or fifth harmonic component percentage here. We can check above the set value and lower the set value, and it will give you the okay. So here 30% waveform, relay will not trip. Here after adding this, there is a option to run this transient. We save the data. Now I have reduced this uh, one component to 10% as a if it is a if you want to check the cross blocking function, it is working or not, then in that case you have to reduce one component to less than the setting value, other two higher than the setting value. So if cross blocking is enabled, then it will not trip. If cross blocking is not enabled, then it will trip. So we can verify. You can see from the graph also. So the state-wise option. There is a null gap detection feature also. If there is a gap, then it also detect. So I'm not going to this. So I think all three method is clear. Now you can do the testing of harmonic testing of differential relays. Fifth harmonic is also the same. So the testing feature is same as Rajan has already explained first day, that it is mostly in generator transformers we consider, but mostly you will find it is enabled in all other transformers also. General practice they put 35% values. So in any case it is not generating, so it will not block anyway. So it is a standard to put the 35 setting 30% of the fifth harmonic in the transformer. So we should have to test it while you are on site. So use the same method. Everything will be same. All the three method is applicable to fifth harmonic as well. So the same way here, instead of 100 hertz, we have changed it to 250 hertz. So these are the method. The same thing. There is no difference in this testing method. So in the software, you will find that in ComTrade file also you can analyze how much different components available in any relay software. Either it is ABB, Wavewin, or Sigra, Siemens Sigra. So every relay has this analysis component. You can use that to analyze the fault DR also. If you are testing, if you want to analyze in the relay, then you can extract the fault DR and see the different components. Okay, so this is for this differential protection. If any question till now, then you can ask. Otherwise, I may demonstrate for few things what we have done. May we start the line differential protection. In the last session, we can explain all these things. Okay. So I also have one other different relay manufacturer representatives. 5 minutes left. Okay, so maybe after
Lunch.
Okay, so you can then ask some questions if you have anything other than differential also. If you have any question related to protection. Else, we can go for lunch, then we can continue.